Hey everybody, before we start the next examples that we're going to work on when it comes to graphing rational functions and finding limits of rational functions, it's going to be important that we do a quick review on how to graph a quadratic equation or a quadratic function when it's given to us in standard form. Traditionally, we would graph a quadratic function from its vertex form. Vertex form is what we commonly use to figure out the transformations. Transformations include vertical and horizontal stretches, compressions, and reflections, as well as horizontal and vertical translations, which are where we shift our graph either to the left or right, or we shift our graph up or down. So that form is much nicer. What would that look like? Well, a quadratic function, the name of the equation, would be describing, obviously if it's a function, it passes the vertical line test, something of the form y equals a x minus h quantity squared plus k. Maybe you also could look at this as a, still on the outside, that's still your vertical stretch, compression, or reflection, only vertical though. Maybe we look at a b value, x minus h, close, squared plus k. We don't normally look at that b value. We end up squaring the b value to get it outside of these main parentheses right over here. So we end up squaring this b value and multiplying it by that a and making a new a value. So we only need to focus on our vertical stretch or compression. We don't need to worry anything about the horizontal, and we don't deal with a horizontal reflection when it comes to quadratics because these are symmetrical. And if you were to reflect it over its axis of symmetry, that's the axis of symmetry, so enough said, right? Nothing would really change. This is what we would look at as being in vertex form, probably more often the first one, but sometimes we see it in standard form, which is ax squared plus bx plus c. Now, let's not get twisted and confused here. And a are all the same a. However, that b value and that b value have nothing in common. I use b for this. You don't normally see a b at all, but this b and this b are not the same value at all. Okay. If you were given standard form, you would traditionally, what you would do is you would rewrite this in vertex form by a process known as completing the square. And after you complete the square and have it in vertex form, you just graph from there. But after completing the square so many times, they were like, well, every time we complete the square, our h value or the x value of our vertex ends up being this, and we can just get the corresponding y value by doing this. What do I mean by that? Well, if you are given standard form as opposed to vertex form, okay? Here, the vertex, really at either of the first two, can be found at h comma k. Remember, this has a minus sign. If it were minus 4, you would go to the right 4, so it's positive h. But this plus k, it is what it is. So if it's plus 4, our y value is up 4. Great. Here, our vertex, and we'll save that for another video, another day, where we will derive this formula. There's a couple ways we could derive this. But our vertex can be found at negative b over 2a, comma. Now, I called this y right over here. When you know it's a function, another thing you can call your function, instead of just y for the output of the function, we can call it f of x. We like f of x because it allows us to say our y value at blank. So I'm going to write f of, so my y value at negative b over 2a. So I'm going to darken that parenthesis and that parenthesis right there around my vertex. opposite of b over 2a, whatever that becomes, that is the x value of my vertex. Then I take that value and plug it in, fill it in for x into my function, and that gets me the output or the y value of my vertex. In order to have a vertex, which is a point, we need a full, complete ordered pair. In addition to being the vertex, the equation x equals negative b over 2a, if I write it like this is an equation. This is an equation of a vertical line. Anytime you have x equals a number, that's an equation of a vertical line. When you have an equation y equals a number, that's the equation of a horizontal line. This equation of a vertical line represents the axis of symmetry. So when we have our parabola drawn, parabola is the name of the shape, the graph, the picture of a quadratic function. When we have our parabola shape, we can draw a dashed line, dash, not solid, a dashed line through the center of that parabola or through the vertex of that parabola, which acts as our vertex of symmetry. And that means either side is a reflection of the other. They are completely symmetrical. Parabolas. A parabola is also not restricted to being only vertical, opening upward or opening downward as functions. They can be rotated on an axis. We would probably use some trigonometry, right, to do a little tilting there. Or a little easier, we could quickly work with parabolas that are completely horizontal, either opening to the right or to the left. And we learn about those in a unit called conic, C-O-N-I-C, conic sections, section meaning like a cross section. So that's for another day as well. One other thing from standard form. Well, I should also maybe want to label that as standard form, and then obviously these vertex form. Okay, now the C value. The C value is very similar to the B value in a linear equation, y equals mx plus b. That constant, without an x, at the end of our equation, when we write them in descending exponential order, will always be our y-intercept. The reason it is always our y-intercept, not always the last number, because if it's with an x, it's not the y-intercept, but the constant at the end, okay? Why is that the y-intercept? Well, think about the y-axis. What does every point on the y-axis have in common? 0, 0. Go carefully because this is where we make mistakes. 0, 1, 0, 2, 0, 3, 0, negative 1, 0, negative 2. Well, what do they all have in common? They all have x equal to 0. Remember, x equals a number is a vertical line. So the equation of the y-axis is x equals 0. Similarly, the equation of the x-axis would be y equals 0. In order to find a y-intercept based on this information, for any equation, in order to find the y-intercept, you plug in 0 for x, and you solve for the corresponding y value or values. If it's not a function, you could have more than one y-intercept. So if I fill in 0 for x, adios, adios, we're only left with that right there. That's why C is always your y-intercept. So this information here, knowing it's symmetrical, knowing how to find the vertex, and knowing that C is the y-intercept is all very helpful with graphing. We should know if A is greater than 0, we have it opening upward. The end behavior is up and up, you may remember. And if A is less than 0, we have it opening downward, or the end behavior is down and down. We will get into a whole conversation about end behavior and how that really relates to limits. So that's also important. And what else did I want to go over? Oh, one more thing. Now, squares. The parent function for all quadratics is just x squared. Classic, beautiful, love it. Okay. We're going to graph this, but discuss my favorite little secret weapon, little pattern that really saves the day and has you draw incredible, perfect parabolas every time. What is that pattern? Well, let's think about number squared. If x is 0, we're going to go through the integers. Integers. Don't be afraid of the word integers either. Integers are whole numbers, including 0 and negatives. Well, 0 is a whole number, but including the negatives, they're not decimal amounts of anything. So it's like 0.0 of something, you know? So 0, 1, 2, 3, but what about -1, -2, -3, and so on, right? So we're going to fill in the integer values for x, and we're going to see what happens with the y values. And we're going to look for a little bit of a pattern, the way an elementary school aged kid would do it. So we also just spoke about how these are symmetrical over their axis of symmetry. In this case, if I did do -b over 2a, y equals 1, x squared plus 0, x plus 0, I would get -b over 2a would be -0 over 2 times 1, -0 over 2, which is 0. So that is actually my axis of symmetry. It's going to be right at x equals 0 or the y-axis. What that means is if I plug in 1 or if I plug in -1, I'm going to get the same output. So that's why you might see people only go on one side and then just mirror image the other side. All right, so if I plug in 2, I'll get the same answer that I would get if I plugged in -2 and so on. So I'm just going to write down a few of these. You should know these numbers by heart, but do you ever stop and think about the really cool pattern that exists between all of the perfect squares of whole numbers or integers? What is 0 squared? So I'm filling in 0 for x, 0 squared, 1 squared, 2 or -2 squared, and so on. Oh, I'm smart. This is what happens when you try to talk and write at the same time. And what I'm going to do now is we're going to ask ourselves, what would a kid notice, a little kid, if you ask them, like, find the pattern, you know, how far apart are these numbers, right? Well, they're not going to be like, oh, 0, 1, 4, 9, you know, that's just a list of all of the perfect squares. No, that's not what a kid is going to say. Let's not be ridiculous here, right? What would they notice? They want to know, like, maybe how much is it going up by? To get from 0 to 1, we add 1. We add 3. We add 5. What do we notice about the distance between, or the difference between, each of the perfect squares? Well, the next perfect square is the next odd number of units away from the previous perfect square. Okay, so that's going to help us draw. How is that going to help us draw? My vertex is at 0, 0. Promise, okay? To get a perfect parabola every time, as long as a is 1, we will follow this pattern. Anything else, we'll stretch or compress as necessary, but I'll go out 1. As x gets bigger by 1 in either direction, my y value will increase by 1, or my output, my function value. Out 1 again, up 1, 2, and 3. 1, 2, and 3. Out 1 unit again. This is special for parabolas. You can't try to do this on everything. 1, 2, 3, 4, and 5. 1, 2, 3, 4, 5. Out 1 and up. 1, 2, 3, 4, 5, 6, and 7. Sorry about that, a little squished. Then all you do is, you draw as best as you can. You connect these dots, got arrows at the end, and you have a pretty nice looking parabola. Not too narrow or pointy, not lumpy, not too fat. Looks pretty good to me. So there, we're up 1 unit, add 3 more, now we're up 4 units, add 5 more, we're up 9 units, add 7 more, we're up 16 units, and so on. All right, there we have 1, 2, 3, and 4, and the same on the other side. All right, so that's phase one of graphing a parabola. And in the next part or the next video, I am going to do a really important example that will be relevant to the example that we're going to do in the next part of our limit lesson. Okay, so we reviewed how to graph a parabola. Next, we're going to do a real example. Then after that, we're going to see how that example will come up in a limit of rational function example. Hope this was helpful. If you understood and you remember all this stuff and you enjoy this little pattern, thumbs up. If you hate this and thought it was stupid, thumbs down. Have a nice day.